Hey guys, in this lesson we're going to go through an induction proof exercise which involves series, and we're going to talk about the simple recipe that works every time you're tackling an induction proof which, as I said, involves a series, a sum of terms. Now, do you know that all induction proofs, they always involve the same 5 steps, which is the propositional function, then we have the base case, the inductive hypothesis, the inductive step, and then lastly we write the conclusion. We actually vomit the conclusion because it's always the same thing. It's very similar. However, for different types of induction proofs, meaning series, derivatives, integrals, divisibility, the 4th step, which is the inductive step, it changes between these types. So we're going to talk about what to do exactly in this 4th step, which is the inductive step of an induction proof, which involves series, that will put you in the best position possible for always nailing these types of exercises. Okay, so let's get to it. All right, so the exercise that we have here is to use the principle of mathematical induction to prove that the sum of I times I plus 1, the series, which is composed by the product of I times I plus 1 when I varies from 1 to n, is equal to 1/3 of n times n plus 1 times n plus 2. So right now, the first thing I want to do, and the first thing that I recommend students to do, is to not leave the sum where it is or how it is. Expand it, see what the first terms are, so you get a full picture of this proof that you need to go through. Okay, so let's do that right now. So the first thing we need to do is to write the propositional function by replacing I between 1 and n. So replacing I by 1, by 2, and then ultimately by n on the left hand side of this equation. We have 1 times 1 plus 1 plus 2 times 2 plus 1 plus 3 times 3 plus 1, all the way up to n times n plus 1. And we need to prove that this is equal to 1/3 n plus 1, n plus 2. So this is the propositional function. We pretty much rewrite what's given to us by the exercise. And in this case, we're removing the sum notation, the sigma notation. Step number 2, let's go through the base case. And given that over here, we're talking about positive integers starting with 1, of course, the base case should be the propositional function calculated when n is equal to 1. We're going to do that on the left-hand side, and we're going to prove that by substituting n equals 1 on the right-hand side, we get the same thing. So on the left-hand side, we have this guy, which is 1 times 2, the first term of this expansion, which is equal to 2. And on the right-hand side, we have 1/3 times 1 times 1 plus 1 times 1 plus 2. That means 6/3, aka 2, given that LHS equals RHS, so left-hand side is equal to the right-hand side. The base case, it holds. Step number 3, the inductive hypothesis. We pretty much take the propositional function and we replace all the n's by k's with one small comment after that, which is for some k, which is a positive integer. That's what we're going to write right now. So we're going to take this and we're going to replace all n's by k. And then we have this equal to 1/3 of k, k plus 1, k plus 2. We're going to assume that this is true for some positive integer k. And there we go. All the easy marks that we could get, roughly 30 to 40% of the marks, they're here. Let's say 30, 35 actually, they're already here. So there's no excuse to score 0 out of something in an induction proof exercise. There's a lot of marks over here. Of course, I don't want you to score 35% of the exercise. We want to get through the whole thing. That's exactly the point of this tip that I'm going to give you, which is how to do step number 4, which is the trickiest one in any induction proof exercise, which is the inductive step. We're going to start by writing p of k plus 1, which means that we have 1 times 2 plus 2 times 3 plus all the way up to k times k plus 1. And we're gonna go one iteration more. So k plus 1 times k plus 2. And on the right hand side, we're gonna take this and replace all the k's that we see by k plus 1 in all of these. Therefore, for the inductive step, we need to prove that this is equal to 1/3 k plus 1, k plus 2, k plus 3. But again, this is the hardest portion of an induction proof exercise. Now, specifically for induction proofs that involve series, the algorithm that you need to go through, the process is the following. You're going to start with the left-hand side of p of k plus 1. You're going to take p of k and substitute it there, the right-hand side of p of k, and substitute it there on the left-hand side. And ultimately, you should simplify as much as you can in order to get to the goal, in order to get to the right-hand side of p of k plus 1. Let me write that down. So again, in the inductive step, you start with the left-hand side of p of k plus 1, and by replacing p of k, you should get to the right-hand side of p of k plus 1, which is your goal. Now, this is the simple recipe, to get the fourth step of an induction proof with series correctly. I just organized everything so we can go through that process together. So we're going to start with the left-hand side of p of k plus 1. Therefore, left-hand side is equal to this. And given that we know that this sum is equal to 1/3 k plus 1, k plus 2, because we're assuming that that is true, we're going to replace it right here, giving us 1/3 k plus 1, k plus 2, plus k plus 1, k plus 2. Now, the first thing that we can do is to write 3 as a common denominator. So we have k plus 1, k plus 2, plus 3, k plus 1, k plus 2. Now, we have two common factors right here. And given that these are common factors, we can rewrite the expression as removing these common factors right here, k plus 1 times k plus 2 times k plus 3. As you probably noticed, you're required to have some pretty good algebra skills for induction proofs. On the last step, we got exactly where we were trying to get, right? Which is 1/3 k plus 1, k plus 2, k plus 3, which is equal to the right-hand side of p of k plus 1. And there you go. We're pretty much done. We're only missing the conclusion. So let's vomit the conclusion. Given that p of 1 is true, and that p of k plus 1 is true whenever p of k is true for some positive integer k, by the principle of mathematical induction, you can write PMI, that's fine. P of n is true for all positive integer n's. And there you have it. This is the simple recipe to ace induction proofs with series. What is the recipe again? The recipe is starting with the left-hand side of p of k plus 1 and using the substitution from p of k, you get to the right-hand side of p of k plus 1 by factoring, manipulating this expression in order to get to the right-hand side of p of k plus 1. That's how you deal with inductive proofs with series.